I'd like to introduce Bill Daly from Nvidia. I'm really excited that he's with us here today. And Bill, thank you very much again for volunteering to come on our program and share your talk with us and our members.
Thank you. Let me share my screen here. Oh. So I'm really pleased to be here. Thanks for the invite. Let me get this into slideshow mode. And I'm going to spend some time telling you about what I've been working on for the last many years, which is deep learning hardware as part of my job at Nvidia. And I'll start with some history and then move forward to what we're doing now and give you a little glimpse of the future. But let me start with applications. Unless you've been hiding under a rock, you've realized that pretty much the whole world is being improved through deep learning. This is in the internet. When you go online, your images are automatically classified and searched. There's render systems that are suggesting what you buy when you do online shopping. There's all sorts of language translation, language tools. Very often when you do a chat with some merchant's customer service facility, it's actually not a human you're talking to. The chatbots are getting good enough. It's hard to tell which ones are human and which ones are chatbots. It's revolutionizing medicine. You can look at images, be they X-rays or CT scans, various things, and do diagnosis pretty much as well as medical professionals can. You can also mine through medical records, and if you're presenting a certain set of symptoms, do a huge amount of data mining and suggest what the problem may be and what treatment might be indicated. It's completely changing the media and entertainment industry in many ways by crawling through video and also by synthesizing videos. We now have generative adversarial networks that are good enough they can synthesize, people talking, people performing, various, stunts, dances, whatever, and it can be hard to tell the real thing from a fake. They're everywhere in security and defense, and a big thing at Nvidia is autonomous machines. We have a huge autonomous vehicle program, about 3,000 people working on it, where we're using deep learning at every stage of the pipeline, starting with our perception. It's better than human perception. I'll talk a little bit about that lately. It goes into prediction. We use deep learning to predict, what the various actors in the scene are going to do next, both people driving cars, pedestrians on the road, animals, whatever. And then we use deep learning in our planning process as well to help pick, what to do next. To give you an idea of how good it is and the influence that deep learning had, this is a slide that shows progress in computer vision. There's a competition called Imagenet that's been going on for a number of years. It was originally organized by my Stanford colleague, Fei Li, where up until 2012, it had always been won by people. This is the whole computer vision field, was people designing essentially hand-designed feature detectors to try to interpret images. And that had kind of plateaued out at around 74%. In 2012, Alex Kruszinski, using 2 Nvidia GPUs, developed a deep network called AlexNet that in 1 year made more progress than the previous 4 years of hand-coded computer vision algorithms put together. And the progress continued year after year after that as deep learning models matured, to the point that by 2015, it had exceeded human performance in this classification task. By human, I don't mean the average human. The average human is probably way down here somewhere, because this task involves classifying 15 different breeds of dogs, and I don't know half of them, so I would flunk. This is the human who curates the data set. So it had been able to exceed the human who curated the data set's performance on that task. That task is classification. This is a slightly different task. This is detection, where you find things in the image and label them. And you see, this is what a typical computer vision system will do to find a car, a dog, a person, a horse, and so on. It's done similar things for natural language processing. And the really cool thing about natural language processing is it can be self-supervised. A lot of the vision systems have to be sort of bootstrapped with manually labeled images, whether they be for classification or detection. People have been able to take huge data sets of text, Wikipedia, Reddit, other online repositories of text, and feed them through neural networks where they delete words and ask the neural network to fill in the words. These are neural networks that are called transformer networks because of how they apply attention to selectively look at certain parts of the speech and not other parts. And they'll basically fill in the missing piece and then grade it as to whether they got it correctly or not. And in doing so, they not only learn language very well, but they wind up learning a lot about what the language is talking about. And people can then build question answering systems out of these things once they've been trained in this unsupervised manner. GPT-3 is one of the larger ones that has been trained by OpenAI. At Nvidia, we collaborated with Microsoft and produced one called Megatron. And they're both capable of answering pretty general questions, almost as well as humans are at this point. They can also translate between languages quite well. And interesting things happen when you combine language models with visual models. You can have interactive shopping experiences where you can hold up an image and say, I'm looking for something that would go well with this lamp, say. The image network would process that lamp, figure out what it is. The speech network would process your speech, figure out what you're asking for. A recommendation system would then figure out what things would go well with your lamp. It would then feed that back to you with a bunch of suggestions for what to buy. And this is becoming the future of commerce in many ways. These recommender systems are probably among the most important of neural networks commercially. They're basically the engine of the internet. Anytime you go to online shopping to Amazon or other sites, it's a recommendation engine that's deciding what things are presented to you. When you go to Netflix, it's a recommendation engine that suggests which movies you watch based on what it knows about you and what it knows about the movie you've asked about, and then it will suggest other things. Whatever it is you're shopping for, when you get ads presented to you, they're suggested by recommenders. And for all of these tasks, what's really going on is that we have gobs of data. We use these data to train networks. We can then use that network to gain insight about a particular problem, whether it's recommending a product to buy, whether it's guiding a self-driving vehicle, whether it's diagnosing a medical problem, and that creates value. And because there's a tremendous amount of value being created here, deep learning really has revolutionized almost every aspect of how we live, work, and play. And if there's an aspect that hasn't revolutionized yet, it will in the very near future. Now, what isn't widely appreciated is that this revolution in deep learning has been enabled by hardware and is being paced by hardware. There are really three critical ingredients to make deep learning work. The first are the models and algorithms. This is a depiction of AlexNet, the deep learning model that was used to sort of really make the first breakthrough in computer vision. But these algorithms and models have really been around since the 1980s. Convolutional deep neural networks, convolutional neural networks, training them with stochastic gradient descent and backpropagation. The first papers on all of those topics date to the 80s or earlier. The next ingredient after the algorithms and models is data. You need lots of data to train these networks. But large labeled data sets were around by 2000, 2005 at the latest for things like Pascal and Imagenet coming online around those times. The real missing ingredient, you think of this as sort of the fuel in the air, the spark that ignited the current revolution, was having hardware fast enough to train these models on this data in a reasonable amount of time. And reasonable amount of time for a lot of tasks is about 2 weeks. The original AlexNet was trained on the Imagenet data set of roughly 1 million labeled images on a pair of Kepler generation GPUs in approximately 2 weeks. And since then, the models have gotten more complex, the data sets have gotten much larger and richer, and hardware has been hard pressed to keep up. To give you an idea, a metric of how hard it is to train a model is how many petaflops per second times days it takes. So if you have a supercomputer that's a 1 petaflop supercomputer, how many days on that computer it would take to train a model? And AlexNet started off here at 10 to the minus 2, because Kepler is nowhere near petaflops, and so 2 weeks on that was 10 to the minus 2 petaflop days. ResNet was a couple orders of magnitude more just a couple years later, and that was sort of the progress in vision networks. Language models, since we moved to transformers with BERT, have been on a much steeper path. In just a 2-year period, they've gone up over 3 orders of magnitude in training. So now it's taking on the order of 10 to the 4th petaflop days to train a model like GPT-3. And OpenAI is working on GPT-4, which is going to take even larger amounts of time. But this crisis in deep learning, where the demand for training has been exceeding what we're able to provide, has led to things like Facebook limiting their language model based on how much GPUs they can get. This is something that for us is actually good, because it's led, let me advance the slide here, to have them buy more GPUs. So they're actually building right now a supercomputer. This is a headline from January with 6,080 of our latest Ampere GPUs. And I think that as they build more powerful models, they're going to need even more. The downside of this is, as an environmentalist, I'm very troubled by the fact that running these supercomputers to train these models puts out a lot of carbon into the atmosphere. Most of the data center customers actually do a pretty good job of offsetting this with various type of carbon credits and offsets. But we're working very hard to try to minimize the energy footprint of training these deep learning models. So let's ask the question: if Moore's law is dead, and this is a chart from John Hennessy and David Patterson, two Turing Award winners from Stanford and Berkeley, respectively, who basically are showing that CPU performance is no longer scaling. How is it that we can continue scaling compute performance so as not to gate progress in AI? Let me start with some history about how we got to where we are, and then I'll talk about how we'll scale going forward. So this is the past part of deep learning: past, present, and future. And what I'm going to show here, I'm going to walk through each point on this graph over the next couple of slides, is how we got from where we were with Alexnet in 2012. That was on a Kepler 20 GPU. That is 3.94 teraops, to where we are with Ampere at over 1.2 petaops of performance. That's an improvement of over 317 times in 8 years. And that will give some insight into where performance and efficiency in deep learning hardware comes from. So let's start with Kepler. This is a GPU we designed before it taped out in 2012, which means most of the architecture was pretty well finalized in 2010, 2011. And that was a period of time when deep learning was really not that much on our radar. I had one project in Nvidia research, what actually turned into cuDNN, running, trying to replicate the Google experiment of finding cats on the internet on GPUs. And that wound up, actually sort of kicking everything else off. But at the time we designed this GPU, it was designed mostly for doing computer graphics and a little bit for doing high performance computing. And so the primary arithmetic in it was FP32, 32-bit floating point, and it had about 4 teraflops of 32-bit floating point performance. So when you did deep learning on it, you used 32-bit floating point because that's what it had. And actually, Google later wrote an article about their TPU-1, which they compared to Kepler, even though it was many years after Kepler. And they claimed that their big advantage was due to specialization. Actually, almost their entire advantage could be attributed to the difference between FP32 and Int8 in terms of raw efficiency. So that was Kepler. Moving on, a couple of years later, we came out with our Maxwell and Pascal generation. And here we had more than doubled our FP32 performance. More importantly, we put in support for FP16 because we'd realized that essentially all inference and almost all training could be done with lower precision floating point. And I'll point out that the energy of an operation, and particularly a multiply operation, goes quadratically with the number of bits. So going from FP32 to FP16 cut the energy of doing these by a factor of 4. And we also introduced dot product instructions. FDP4 and HDP4 were half full precision and a half precision 4-element dot product instructions, and that acted to amortize the overhead of fetching and decoding instructions over more work. So we're getting more payload and less overhead as we do this work. We also added HBM memory. These things you see on the side are inductors. Those aren't memories. The memories are these 4 rectangles on the interposer around the big GPU in the middle. And HBM memory gave us enough memory bandwidth to keep up with 20 teraflops of FP16 performance. And to allow us to scale this into bigger systems, we took a technology we developed in NV research called NVLink, which allowed you to connect a number of these Pascal generation GPUs together at very high bandwidth. So that gave us another point on the graph. We've moved up a little bit here. But a big jump came with Volta just about a year later. Because with Volta, we finally realized we needed to put in special purpose hardware for deep learning. And that special purpose hardware we called tensor cores. So whereas Volta bumped the FP32 performance by about a third to 15 teraflops, it increased the FP16 performance by almost an order of magnitude to 125 teraflops. And it did that by introducing a special matrix multiply unit. And we exposed this matrix multiply unit in the form of an instruction, half precision matrix multiply accumulate, which took 2 4x4 16-bit floating point matrices, multiplied them, and accumulated the result into an FP32 matrix. We also had the second generation HBM. Those are these 4 squares. So each of these squares is actually a stack of 8 memory chips. And they give us 900 gigabytes of memory bandwidth, enough to keep these 125 teraflops fed. And to allow you to build larger systems, we introduced our second generation NVLink with 300 gigabytes per second off each of these GPU modules. And we introduced NVSwitch to allow you to build systems where you could connect large numbers of GPUs and have them share memory as if they were a single GPU by doing load and store instructions. A couple of years later, our Turing generation, the Q8000, is a Turing generation quadro board. It introduced integer tensor cores, because for inference, FP16 is more precision than you need, and you can cut the power another factor of 4 by going to int8. So we have basically the same 130 teraflops of FP16 performance as Volta, but we doubled that for inference for int8 with an integer matrix multiply accumulate instruction. Orthogonal from deep learning, we also introduced our hardware for ray tracing in this generation, the RT cores, which I'm particularly proud of. That's another project that started in NV Research. And then the big jump here to Ampere is a culmination of a number of things. The big one is sparsity. It turns out that, like your brain, real neural networks don't need to be densely connected. Something that my student Song Hong and I wrote a paper about in 2015 at NeurIPS. But we found for the next 5 years, it was very hard to figure out how to actually take advantage of this, because sparse networks are irregular, and irregularity causes inefficiency. And so it wasn't until Ampere where we came up with structured sparsity that we're able to really turn the corner and get a really good return on sparsity. We also introduced some new data types, what people call brain float 16, which is an alternative 16-bit floating point format with more exponent bits and fewer mantissa bits, and TF32, which is basically the exponent of brain float 16 and the mantissa of FP16. It's actually a 19-bit format, but we put it in a 32-bit container. And this allowed us to train some networks that we were unable to train with either FP16 or bfloat 16 using TF32. We had up to 624 teraflops of either of the 16-bit formats and 1.2 petaops of int8. It also had int4 and int1 modes. You can get up to 2.5 teraops of int4. But at the time, we actually now understand how to use this a little bit better. At the time, we had trouble getting real networks to work well at int4. And a good figure of merit is the number of teraops per watt. And I'll talk more about this later. Ampere clocks in at around 3 teraops per watt on dense int8 and about 6 teraops per watt on sparse int8. So this cartoon illustrates how our structured sparsity works. We start out by training a network with dense weights. This is the matrix of weights. We then basically take the low valued weights and set them to 0, and then fine tune the network to have it sort of work better with those forced to be 0. And actually what Song and I showed in our work back in 2015 is you can do this without any loss of accuracy in the network and actually take out way more than half the weights. For some networks, you can take out 90% of the weights. We then compress out the non-zeros and put a little code word in to say which ones are the non-zeros. And we use that code word to select which activations to multiply by these weights. The activations that would have been multiplied by zeros just get tossed away. We take just the activations we need, multiplex them down into a dense vector, multiply that dense vector by the dense vector of weights, and that gives us our dot product, which we then accumulate into the output activations. And using this, we've basically been able to double both our performance and our energy efficiency on deep learning applications. So if you want to ask, where did this 317 times come from? Most of it came from number representation. Remember, going from FP32 to int8 is a factor of 16 difference in efficiency. Another big part came from complex instructions. When we started out, the overhead of the instruction fetch and decode, even though GPUs are very efficient because they amortize one instruction over 32 lanes of our SIMT SMs, the overhead was many times that of the instruction. By the time we got to the IMMA instruction, the overhead was about 15% of the total. We were as efficient as a dedicated deep learning accelerator. And then a little bit came from process, but very little. It's probably less than a factor of 3 came from scaling from 28 nanometers down to 7 nanometers, getting to the A100. Let me drive home this point about specialized instructions a little bit. If you look at the most specialized instruction we had in Kepler, half precision floating multiply accumulate, The energy of that instruction, I'm normalizing everything here to 45 nanometer numbers to have one thing to compare against, was about 1/20th that of the 30 picojoules needed to fetch decode the instruction and fetch the operand. So we had 2,000% overhead, much like many big corporations or governments, we were dominated by overhead. Going to dot product instructions, we did 4 times as much work for the same amount. Now our overhead's only 5x. But once we added the tensor cores, the overhead was really almost negligible, roughly 20% in Volta and 15% in Turing and subsequent GPUs. So by building instructions that do a lot of work, you can amortize out that overhead of the instructions. Another thing we did, it isn't really reflected in the graph at all, is by building NVLink and NVSwitch, we enabled people to scale up. And these large language models are typically trained on clusters of many thousands of GPUs. The new Facebook cluster is a little over 6,000. A very popular size for a while was about 4,000 GPUs, which is what this thing is. These individual boxes, 5 in each rack, are A100 DGX boxes with 8 amperes and an NVSwitch in each one of them. Each one of them shares memory locally. And then using our Mellanox InfiniBand switches, we connect that whole cluster together and have a very efficient supercomputer for deep learning training. Now, complementing our GPUs, and actually in many ways, this is kind of like the farm teams cultivating players to move up to the majors being the GPUs. We've been developing a range of accelerators. All of these deep learning accelerators are basically matrix multiply units fed by a memory hierarchy. But there's a lot you can do right or wrong in how you both build those matrix multiply units and how you build the memory hierarchy that can make orders of magnitude difference in efficiency. The thing to realize is that different operations cost different amounts. 8-bit integer operations are really inexpensive. These are 45 nanometer numbers that are due to a paper Mark Horowitz had at ISSCC in 2014. So it's just 30 picojoules in 45 nanometers and under 10 in a modern process to do an 8-bit add. And even an 8-bit multiply is relatively inexpensive. As I said, the cost of multiplies increases quadratically with the number of bits. But the thing that you really realize when you look at this chart is reading memory is super expensive. And it isn't on this chart, but moving things, even a very short distance is very expensive as well. Communication really dominates energy. And realize this is a log chart here. And so the way to think about this is it's really critical to keep things local. If I read something out of a local SRAM, that's 5 picojoules per 32-bit word. If I have to go globally on chip, it's an order of magnitude more expensive. And if I have to go off chip, even to a very power efficient LPDDR DRAM, it's another order of magnitude. It's even more if that's a SDDR. So there are a bunch of things we can do to try to reduce this both data movement and the amount of work that needs to be done. And these are common themes in improving the efficiency of deep learning. The first is pruning, and I'll refer you to the paper that Tong Han and I wrote in NeurIPS in 2015, where you take this neural network. Before pruning, it's dense. Every neuron of one layer is connected to every neuron of the next layer, and then we just not randomly, but in an intelligent manner, lop out neurons. And what we were able to show is that you can do this actually quite effectively without affecting accuracy. It was a real challenge for many years until Ampere to actually get real gains from that. So data representation and sparsity are 2 of the common themes we'll be seeing going through here. Our effort in accelerators really began with the NVDLA. This is a project we started around 2013. Like most deep learning accelerators, its core was a big matrix multiply array. We had an array that could do 2,048 integer multiply accumulates per cycle, or 1,000 either int16 or FP16. What made it sort of unique is even at this point in time, we realized the importance of sparsity. And so we basically stored all of the weights and activations in sparse form using a bit vector encoding. And then as we read them out of this unified buffer, decompressed them into the MAC array. We also did what we call data gating, so that if a weight was going to be 0 as we were decompressing it, we didn't actually send the weight. In fact, we didn't even toggle the data lines. We left them at whatever value they were in the previous cycle and sent a 1-bit line saying, I am a 0. And this saved the energy of toggling those lines to 0 and then toggling them back to the next number. And that actually gets most of the energy gains of sparsity just by doing those 2 things, doing all your storage and data movement sparse, and then doing data gating of the MAC array. Another neat thing we did was we put native support for Winograd transforms in here. As everybody knows, when you're doing a convolution, say an n by n convolution, the complexity of that is n squared if I do it in the spatial domain. But if I do it in the frequency domain, it's one. It's a convolution is a pointwise multiply in the frequency domain. So if you do a Fourier transform, do a pointwise multiply and inverse transform, that's the equivalent of a convolution. Here we do a Winograd transform instead of the Fourier transform, but the principle is the same. The next project we had, this was what I did at Stanford with Sung Han, was to build an accelerator that handled sparsity well. And to do this, we basically built hardware that walked the pointer structure for a compressed sparse row representation. And we also were experimenting with data representation. And our theory at the time was the best you could do was to use a code book of scalar quantization. And what we showed in a paper in ICLR in 2016 is that you could train that code book through backpropagation and come up with an optimal code book for a given neural network. And it was optimal in the sense that it's the fewest bits to get a certain amount of information content. It wasn't optimal energy-wise, because the problem with the code book is it's energy to look up the code word. And then to be able to represent that code word accurately, your actual math has to be done at relatively high precision. Here we did it with FP16 math. But it demonstrated really the advantages of sparsity in hardware and coding. It had been for a long time thought that if you're going to use the sparse matrix package on a supercomputer, you have to be really sparse. You have to be like 0.1% dense or less. Here we were able to get good numbers with 50% density by basically using special purpose hardware to walk those pointer structures. My colleague Joel Emmer at Nvidia, working with Vivian Z at MIT, developed this Iris chip in 2016. And the real thing it demonstrated was how important it is to tile the computation. You have this sort of 7 nested loop of multiplies that you're doing for a layer of a convolutional network. And if you tile that and map it in time and space right, it minimizes the data motion. And they showed a couple of different tilings, one they called weight stationary, one they called row stationary, that really sort of set the stage for a lot of further research in getting rid of this very expensive communication energy. Our next attempt at sparsity was a chip we did in 2017 called Scnns for sparse convolutional neural networks. And here we moved all the complexity of sparsity to the output side. We basically realized that if we encoded things right, we could just take every weight and multiply it by every input activation. This is sort of the F weights by I input activation multiplier array, giving us F times I things coming out. And then we have a separate computation where we decide where those go, and we do a scatter add into a bunch of buffer banks. The problem is it did a little bit better than dense, but not enough better to really make it worth doing. And the problem is moving the complexity of the output stage is almost the worst place to put it, because we're at some of the highest precision in this output stage, where very often we'll do 8-bit multiplies, but accumulate to 32 bits on the output stage. And the cost of accessing all these buffers wound up really sort of bringing this idea down. We built another chip in 2018. The papers were published in 2019. Our chips had these creative names like Research Chip 18. And this demonstrated a bunch of things. It was like Iris, designed for tiling. And it was tiled at 2 levels. We actually built a multi-chip module with 36 of these chips on the module. And then within each of the chips, there was an array of 16 of them. And so this could scale from a small single chip thing to a 36 chip thing, giving a very wide range of performance. And it was getting around 10 teraops per watt, which is at the time a record. But it really then set the stage for us to actually build a tool to search the design space of neural network accelerators. And we called this tool Imagenet. It was published at ICCAD in 2019. And what Imagenet did is it basically looked at how you could do that tiling, and then various things like how many lanes in your vector map and how many vector maps in parallel, basically the vector size and the number of lanes you would do, as well as what were the size of your weight buffers, input buffers, and accumulation buffers. And then we added a second level of data flow and put in weight collectors and accumulation collectors. And with that second level of data flow, we were finally able to get to the point where more than half of our energy was going into the math, as sort of shown over here. This is with what we call hybrid data flows of weight stationary, local output stationary, and output stationary, local weight stationary, where we basically hold, for example, the weights constant, but then use those collectors so that the outputs don't have to access the large accumulator buffer. And in doing this, you see here, we're about 60% math and the rest being data motion. And that was a big improvement. Results from this magnet, before I even go on to the VS Quant results, have now gotten over 100 teraops per watt in chips that we now have back from fab, and we'll be publishing results on shortly. Another thing we realized with data representation is we've been focusing very much on the representation of a single weight or a single activation, but some good encodings actually want to encode a group of weights or a group of activations. And so we published a paper at MLSys just this past year where we showed that if we use relatively fine-grained groups of weights and encode with them a scale factor. So we'll take, for example, 32 weights and associate it with a scale factor. So we can put the dynamic range of, say, even a 4-bit weight really where it does the most good. We could get performance comparable to FP32 on a lot of these big language models like BERT with no subsequent loss of performance. That's really what's shown here. Both BERT base and BERT large, we're able to get, in a lot of cases, 4-bit weights, 4-bit activations, getting essentially the same performance as using FP32. So let me sort of summarize accelerators, which we sort of view as sort of the farm team for our GPUs. You start with a matrix multiplier. You come up with an efficient data flow that maximizes the reuse from your most local level of memory. So you're not making these big expensive accesses to memory on the other side of the chip. The number of levels of memory and the size of each level of the free variables here, and our tool Imagenet searches over those free variables as well as how to reorder the loops of that tiling to give you the best possible energy efficiency. You then want to play the card of sparsity, using it for compression to reduce the number of references you make from memory. It also increases your effective memory capacity, reduces your communication cost, and data gating, so you're not toggling data when multiplying by zeros. And then with structured sparsity, we can actually get sparse computation. Then the final card we play is number representation. With the EIE, we tried coding, which it does absolutely the best you can do in terms of storage and communication, but it makes the math expensive. Scaling puts the bits where they do the most good. And if we scale by the vectors we did with VS Quant, we wound up really getting about the best representation that we could get, and we're able to get really spectacular numbers on these big language models. And we view this as feeding into what will be in future GPUs. So if we build an accelerator, which is a relatively less expensive thing to do than building a new GPU, it works really well. The scouts are out there, they'll recruit that player to go play in the GPU team in a future year. So let me talk a little bit about future directions. So now I've done past and present, let's talk about future. So if we look at where we are with our sort of 100 teraop per watt version of Magnet and where the energy goes, well, 47% of it is math, and the rest of it is largely memory and data movement. So we want to sort of go back to the things that have been working for us and then a few more. We're looking at better number representation. We're looking at logarithmic number systems as a way of achieving that, and I'll talk a little bit about that. Better tiling for lower memory energy. Circuits to reduce both memory and communication energy. We're still pushing on sparsity. We've gotten some big gains with Ampere, but there's more to be had. And then process will get us a little bit. So let me dive into each of those. So this is sort of an example of a logarithmic number. This is a format we call log 4.3. It has one sign bit that determines if it's positive or negative, and 7 bits that in this case are multiplied by sort of 2 to this value over 8. So this is sort of the integer part. It's 2 to this value, and this is a fractional part. This is the the 8th part. Up from 0.8 to 7/8. And with an 8-bit logarithmic number, you get really good dynamic range of 10 to the 5th, and the worst case accuracy is 4%. Compare that to integer 8, where the dynamic range is about 100. You represent minus 128 to 128, and the worst case accuracy is 33%. Because the problem is the accuracy of a logarithmic number system is a constant percentage of the magnitude represented, except at 0. The accuracy of a integer number system is a half everywhere. And so it's really bad for small numbers. Here's a way to sort of visualize that for those of you who are old enough to have done calculations in college with slide rules. This is a logarithmic number system. If you want to multiply 2 numbers, you take one number, in this case, say, 1.13, and you put, the one on top of that, and then take the other number you're multiplying and read off the answer. And what you're doing is adding two log representations to do a multiplication, because in the log number system, multiply becomes add. The advantage of the error representation is sort of shown here. So log numbers in some places have bigger errors than integers do, but they have bigger errors at the bigger number. This is a 4-bit log representation, L22. And so the big error here is 9%. At the really small error here, it's still 9%. So if you want a 9% error, everywhere you use a logarithmic number system with 4 bits. If you do the same thing with a 4-bit integer representation, the error is a half. And when you get to 1, your error is actually 50%. I think I called the max error here 33% by the biggest. Actually, at 1, you're exactly represented. At 1.5, your error is 33%. And the problem is when you look at where the weights are, they tend to be close to 0, right? So where most of your weights and activations are, they tend both to have somewhat normal looking distributions like this, is where the integer number system has its biggest errors. It's not out here where the errors are really good. So log number systems look really good for representing this stuff. Now, as I said, log number systems make multiplies easy. They make the adds hard. Normally in a log number system, you'd have to convert back to integer, do the integer add, and convert back to log, and that's expensive. But we came up with a clever way of doing it, and because we filed a patent on it, it's now public information. So I encourage you, if you're curious, to look up this patent number, and you'll see what the clever trick is. Let me move on to sparsity. So it's easy to show that you can sparsify networks, and they still work really great. It's really hard to get real energy advantages from that. After you've done the data gating and have taken the low-hanging fruit of compressing for memory and communication, trying to actually reduce the number of arithmetic ops is easily swamped by the cost of irregularity. We've literally built about 5 different accelerators, trying different clever things to try to exploit sparsity denser than the 2-to-1 structured sparsity we have in Ampere. And they've been really swamped by the cost of irregularity. There's a lot of calculation that goes into deciding which numbers you actually need to keep around and feeding them into the right arithmetic units. That results in large multiplexer structures. And glitching is a real problem because you're kind of computing the select inputs of these multiplexers while the data is propagating. You'll very often actually wind up glitching the outputs of the multiplexers many times. This really effectively causes your arithmetic units to do many computations before you finally get the final value and it does the final computation. So both EIE and SCNN gave marginal gains at the system level. Ampere gives us a good solid 2x gain because the structure overcomes these problems of irregularity. But we'd like to do sparse activations as well as weights. There's another easy factor of 2 to be had there. We'd like to go to lower density, down to 25%, even 10% for some networks, rather than the 50% we have for Ampere. So that's something I hope to do in the future. And then there's a lot of things we can do to optimize the memory circuits. We're using kind of standard library memories right now for a lot of these, both accelerators and GPUs. They're small, mostly read memories. So for example, because we're getting reuse out of them through the tiling, we'll load a waiter activation in, and we'll use it 32 times before we overwrite that location. So we want to optimize to make reads cheap, writes can be more expensive. And one way to do that is to basically, rather than muxing things onto a bit line, which is conventionally how these memories are built, is if we give every word its own bit line all the way to the output, we put a multiplexer right at the output. Now, when you write the memory, you energize that word line, but you only do that once. I should say that bit line. And when you read, all you do is switch a mux at the output, and the read becomes very inexpensive. And then because most memory energy is communication energy, we can also take these lines and operate them at less than full voltage swing. Which brings me to some of our communication energy saving ideas. This is a paper we had at ISSCC in 2016. We actually prototype a lot of these circuits on GPUs. I think this went out on a Maxwell generation GPU in a little spare area that was for a test circuit. But the idea was energy in electronics is proportional to V squared. For CMOS things, it's CV squared communicating along here. So the wires have a sort of a constant C. We can't change that very much. But if we take our power supply and we split it, so we send half of our bits on a rail between half of VDD and VDD and the other half of the bits between ground and half VDD, we wind up cutting our power by a factor of 4 and getting down to on the order of 5 to 10 femtojoules per bit from around 40 or 50 femtojoules per bit today. And the reason why we switch back and forth between the upstairs and downstairs is to balance the toggle rate. So the current draw on both of these rails is the same. And that way we don't really need to source or sink any current into this mid rail to regulate its voltage. So almost all the numbers I've given you up till now, except for the 100 teraops per watt one that's out of a 5 nanometer chip, have been for 16 nanometers. Denard scaling, where we're able to lower the voltage as we scale line widths, is pretty much dead. We still have to keep nominal 1 volt supplies almost everywhere. But the capacitance does scale somewhat slower than linear. And going from 16 nanometers down to 5 nanometers, we're expecting around a factor of 2. Now, I've seen a lot of papers in various conferences and the like about analog or optical computing, and the optical computing is analog computing itself. It's just analog computing in the optical domain as well. And these things show great numbers if you just look at the operation. Doing an analog multiply is almost free. You basically have a resistor, if you can get it very accurately calibrated with the weight you want to multiply by. You apply a voltage to it. The current through the resistor is the or the other way around, I guess. The result of the multiply, and then you can sum those currents onto a bit line, and that add is almost free as well. The real problem with analog is that typically in neural networks, you have to both move the data various places and store it over periods of time, neither of which can be done very effectively in the analog domain. So there's an analog to digital conversion required somewhere. And that analog to digital conversion, if you want to have accuracy comparable to, say, an 8-bit integer thing, costs you between 0.5 and 1 femtojoules per Mach, which sort of limits you to sort of 1 to 2 teraops per watt. And this is the people from Mythic, which is a startup company doing analog neural networks, published a paper at ISCC just this last February 2022, and their numbers are actually consistent with that. They're around 2 or 3 tops per watt all in, even once you consider all the overheads. And that's because they're just completely dominated by these A to D conversions. And the optical ones are even worse, because in addition to having to do that A to D conversion, they have to do an E to O and O to E conversion as well. So let me wrap up, and then we'll have a little bit of time for Q&A. So as I said, deep learning is transforming almost every aspect of our lives: how we work, how we play, when we shop, how the recommendations get fed to us. It's making it easy if we go to a foreign country, it'll translate our speech. And anything that it hasn't really affected yet, it will. It's changed gameplay. Reinforcement learning has been able to show master level performance in all sorts of games. I mean, chess was cracked years ago without deep learning. Those were manually designed feature detectors. But deep learning has sort of exceeded that at chess, and has cracked previously difficult games like Go, as well as things like StarCraft. They now have deep learning systems that play expert level at that. To feed this revolution that's going on, we need better GPUs. The deep learning revolution was enabled by GPUs. They were the spark that ignited the combination of algorithms and data. You needed the compute performance to handle it. And then as people have come up with ever more complex models and trained them on ever larger sets of data, we've needed to scale the performance of GPUs to keep up. It's been a tough thing. We've done pretty well so far, going from Kepler in 2012 to Ampere in 2020. We've scaled 317 times. That's been a combination of better number representation. You're getting essentially a factor of 16 by going from FP32 in Kepler down to int8 and even int4 in Ampere. Amortizing the overhead, getting a factor of 20 by essentially making the overhead negligible. Going from single floating point operations to dot product to matrix multiply accumulate instructions in both floating point and integer. Exploiting structured sparsity. What I didn't talk a lot about is, as we've cranked up to doing 1.2 petaops of math in the arithmetic units of the SMs, the plumbing to get all the numbers into those arithmetic units has had to scale as well. And there's a lot of cleverness that's going into doing that plumbing well to make it scale without just really busting the budget on either power or area. As we move forward, we like to use accelerators as a way of experimenting with new techniques, new approaches to sparsity, new data flows, new number representations. One number representation I'm particularly excited about is a logarithmic number system. And so what is the future? How do we keep doubling? Well, better number representations, log numbers, and also doing the VS quant thing, doing scaling over relatively small vectors and numbers allows us to use even relatively low. This may actually make log numbers not necessary. You can do scaling over relatively low precision integers and make them work as well as floating point numbers in a lot of cases. Scaling sparsity, applying it to both activations and weights and to more than just 2 to 1. Better circuits and better process. And with that, I hope we can continue the scaling we've seen over the past many years, because I think it would be a shame if deep learning kind of sort of stagnated where it is today because we didn't have the hardware to take it to the next level. And with that, I will open it up to questions. I am right here on the North Shore of Lake Tahoe in Incline Village.
All right. Thank you, Bill. Great talk. Okay, so for questions, I've got a few here. Let's see. Let me make sure that I am online. I am. So Alexander had posted a question a little while ago. Exponential increase in petaflops per day corresponds to an exponential increase in energy consumption. 2 questions. First, when do you see this development coming to an end? And second, which technology should we pursue if we're interested in sustainability, like carbon footprint, et cetera?
Yeah, so what's counteracted let me try to pull up a couple of slides here real quickly. So what's counteracted, the exponential increase in numbers, but I won't go to slide 2 because I want to flip to another slide very quickly, is shown here. But what's actually kind of matched that is our exponential increase. And this is actually not shown on a log scale, but this is also an exponential increase in ops per watt. And so those two have kind of canceled each other out. So it hasn't actually been an exponential increase in watts. It has been an increase in watts. But the way to think about it is, our GPUs are 317 times more powerful than they were 8 years ago at about the same power. These are all about 300 watt GPUs. So the situation is not quite as dire as just an exponential increase in watts. That said, I think we feel very very responsible that they're, that sort of GPUs are used in a responsible manner and not used to, warm the planet to its end. And so, we have a plan underway to run all of our data centers on 100% renewable energy. Many of our customers do that as well. Where we can't, we buy carbon offsets to offset any non-renewable sources that we do. And I think that's what people have to do. I mean, you have to use the electricity, but you should be generating it in a way that has 0 ultimate carbon footprint.
Great. And we're back to questions. Kaysun has a question. Any comment on quantum processor unit in deep learning?
Yeah, so I'm kind of negative on quantum. It's interesting. One of our members of our board of directors came to me a while back and wanted me to start a quantum group within Nvidia research, and we actually did, but we didn't do what he wanted. He wanted us to be building, various types of qubits and stuff. And instead, we have been spending a lot of time building good simulation algorithms for qubits. And actually, I think if you actually are interested in quantum algorithms, your best bet is to buy a GPU and run our package cuQuantum on it. So deep learning is fundamentally a big data problem. You have to run over, to train an image network these days, billions of images. I think we have many hundreds of billions that we use in training the perception system for our self-driving cars. And quantum computing is fundamentally a small data, large compute. It's leverage, if they're ever able to get there, is that with a small number of qubits, you can't have very many bits in your computation, but you can do exponential computation because you can have qubits in multiple states simultaneously before you collapse the system through observation. So it's not really well set up for deep learning as we practice it today. It also has this problem that they are orders of magnitude away from the accuracy they need in a single qubit, and orders of magnitude away from the number of bits they need to do something useful with quantum computing. Useful quantum computing will require order of 1,000 good qubits, and if you assume they could get like an order of magnitude better, most people are around sort of 1% accurate, 1% error rates in their qubits today. Yeah, that's maybe being generous. A lot of them are like 2 or 3% error rates. But if they could get to 0.1 or 0.01% error rates, another 1 or 2 orders of magnitude, then it would take 1,000 noisy qubits to make one good qubit using surface codes. And people have made things like 50 qubits. So they need to get from 50 qubits to 1 million. So they've got a way to go, and they need to get from like 92% accurate to 99.99% accurate. So they've got a way to go, and I think that's it's non-trivial. People should realize that quantum computers are analog computers. You can't, what makes digital so great is you can do a noisy computation, ANDing 2 bits together or something, and then you threshold it. It's either a 0 or a 1. You can't do that in quantum, because if you say it's either a 0 or 1, you've observed it, you've collapsed the state. So these computations are done in an analog manner. The superconducting ones, by rotating the qubits with microwave pulses. And if that microwave pulse is 1% too long or 1% off the frequency, you have a 1% error. And this all has to be done also in a way where these bits are completely isolated both from one another and from the environment. Because if you couple into the environment, that's an observation as well. And that's what causes decoherence in the order of 100 microseconds in many of these machines.
Interesting. Seems like there's a pretty big impedance mismatch. It'd be interesting to see if there's something fundamental that changes.
I think what it's a really good match for is simulating like quantum things like quantum chemistry. But you still need a lot of qubits, and they got to be better than they are today to get there.
Right. I see. Okay. Venkatesh, thank you for your question. He says, could Bill shed some light on the carbon footprint when running training and inference for large-scale ML models? And what hardware and software changes has NVIDIA implemented for the same? Also, does NVIDIA have any projects in the works for performing training and inferencing on embedded devices?
Yeah, so that's a good question. I think I already answered the first half of that. So we've done this 300x improvement in efficiency over the last 8 years to Ampere, and we expect to continue that. I said Ampere's in the 3 to 6 teraops per watt range. We have prototypes in the lab that are 100 teraops per watt. So there's another factor of 20 in the works that hasn't propagated down into our final GPUs. So we're making it much more efficient to do the computation, especially inference, because deep learning is moving to, it used to be mostly training as people experimented a lot, but now they deploy models and they run them a lot, and it's becoming mostly inference. And we also, in our own data centers, and we encourage our customers to do this in a responsible way and to use renewable resources for running these computations. And then on the embedding one, so we have a whole line of products called our Tegra line of products. We have Orin and Xavier and Altland, and these are made primarily for our self-driving cars, but they're quite powerful embedded processors with both the deep learning accelerators in them, and the latest one has Ampere GPU cores in it. And this is actually what powers the self-driving cars that we run, and that I think almost 100 different manufacturers now use our hardware in their self-driving cars. And it's a real nice platform. And we make these in a bunch of different sizes. We also have a product line called Jetson, which is basically small printed circuit boards that take these Tegra chips, and they're widely used in a lot of different robotics applications. And so we have a big effort to provide the hardware needed to do deep learning in embedded systems.
You mentioned in your answer that there's a lot, it used to be a lot of learning, but now there's more running models.
There's still training, and the hero training runs. I mean, when OpenAI trains another big language model, I mean, they take a 4,000 GPU cluster and tie it up for like 4 or 5 months, and so that's a huge amount of energy. But if you look at what a typical customer does, they'll have a recommender model that, when you go to Amazon and say, I'm looking for, paper towels, it will know your profile and know about paper towels and suggest to you what you're likely to like. And they will redo that model, weekly, if not daily, but they deploy it a lot for every time they redo it. So things are shifting to where there's more inference than
right. Okay. So Suhas says, asks, do you think in-compute memory is going to be important for performance and energy efficient gains?
So that's a really good question. And I think it's really important, for the reason I showed. Let me move to a different slide here, to keep the computation close to memory. And so, it's really important that you don't move the bits very far to do computation on them, because it's really expensive to go out to main memory that's off your chip, or even to go to the other end of your chip. And that's why in our latest version of Magnet, we basically put another level of memory hierarchy with these weight collectors and accumulator collectors. They're literally like forward memories sitting right next to the arithmetic units, so that the bulk of the operations come right out of these guys. What doesn't work well is to try to push the compute into DRAM, because DRAM processes are really optimized to making capacitors. It's truly amazing. These capacitors are, extremely tall on a microscopic scale. I mean, they have aspect ratios of 30 to 1, right? They're, a couple nanometers, I should say a couple, maybe 50 nanometers wide across the bottom, 50 to 100, and, a few microns tall. But because of that, the transistors in a DRAM process are truly awful, and the interconnect in a DRAM process is almost worse. My mental model is it's like designing a 90 nanometer technology. And it winds up being an order of magnitude more expensive to do an add in a DRAM process than it is to do an add in even like a 16 nanometer process. And so I think it's a false economy to try to move the computation into a bulk memory device. I think it is much better to do the computation right next to some small memory that you're going to get a lot of reuse out of. Now, the other thing that people talk about when they talk about compute memory is actually analog computing, where they'll do either an RRAM cell or a flash cell. But rather than using that just to store bits, they'll put the weight in that cell and use the resistivity of that cell to try to do an analog computation of the weight times activation multiplier. Usually the weight's in the cell, the activation gets applied as a voltage or a current, and then a current sums the output. And that works really well until you have to do the A to D conversion. I encourage people to look at the Mythic paper from this year's ISSCC. I think they've done about the best job of anybody I know attempting to do that, and are trying to field a product. But to the extent that you have to go back to digital to store the information or to move it from one place to another, you sort of lose whatever advantage that analog computation gave you, and then some.
Nader Bagherzadeh has a question. Thanks, Nader, for your question. He actually shared machine learning computer architecture enhancements with us in a webinar, Bill, just a couple program events ago. He asks, why not consider systolic arrays as one of your accelerators?
Well, actually, our tensor cores are systolic arrays. I mean, I didn't go a lot into the details, but they're matrix multiply units, and the right way to do a matrix multiply is kind of to march the two things by each other and do the appropriate computations. So we do use actually systolic arrays in various places in our GPUs on the small scale. And the way I like to think about a GPU is it's really a platform to plug accelerators into. I mean, it started existence as a platform where we had some general purpose computing engines, and then we had hardwired units to do raster graphics, rasterizers, texture filters, compositors. And then we added the tensor cores to do matrix multiplies, and those are systolic arrays. And then we added our RT cores to do, a lot of people don't appreciate what they really do. What they really do is they walk a bounding volume hierarchy to search for, where a ray first hits a triangle. And so they're walking a tree data structure and then doing ray triangle intersections. And as we come up with other application areas we think are important, we will put other accelerators in, and many of them will be systolic arrays. I think systolic arrays are a nice way of doing accelerators in general.
Right. Okay. Suhas asks, will GPUs continue to be important for progress in deep learning, or will specialized hardware accelerators eventually dominate?
Oh, I think GPUs will be important for a long time, because GPUs have become specialized hardware accelerators. I mean, if you look at our SMs, we've got this nice programmable unit, but that matrix multiply core is really big. I mean, it's a large chunk of the area that's in there, and that's a specialized accelerator. So the GPUs really have become specialized accelerators for deep learning. But having that programmable engine sitting there and having it be really easy to program with a big ecosystem of software tools is a huge advantage, because these deep networks are changing on a really rapid basis. I mean, it wasn't that long ago where all the language models were RNNs, recursive neural networks, and transformers hadn't been invented. And now all of those RNN models have been thrown out the window, and everything is transformer models. And it requires a certain amount of programming. You still can, if you beat on things hard enough, you can turn everything into a matrix multiply at the inner loop. I mean, when you have a hammer, everything starts to look like a nail. When you have a matrix multiply unit, everything looks like a matrix multiply. But you still need that programmability to sort of do that hammering and getting it into the shape to feed into the matrix multiply unit.
Okay. Muslim asks, do you see any potential for spiking neural networks to replace current artificial neural networks?
Short answer is no. I mean, what spiking is it's a way of representing numbers. And as I showed, a lot of our gains have come from coming up with more energy efficient number representation. But to represent a number with spikes, you're basically repeatedly toggling something between 1 and 0, and you're encoding the information depending on how you think about it, either in the frequency of the spikes or in the interval between them. And those are the reciprocal of one another. But to have a certain dynamic range and a certain precision requires that you have a lot of spikes to represent a number, and that's a really energy inefficient way of representing that number. So I think it's a great way of sort of studying biology, because we know that most brains, not all, have spikes. I forget who I was talking to that told me that, I guess, C. elegans or whatever, the activation potentials in the neurons are actually continuous values and not spiking. It's a great way to sort of build models of actual biological systems and study them. But I think to get really good performance on neural networks for vision or speech or language, we're much better off using really optimized digital representations of those. And some combination of log and VS Quant right now is the best we know how to do.
Dylan has a question. I think you've already answered this with the other question about systolic arrays, but just in case you have anything else to say about how NVIDIA's approach to data flow compares to other approaches such as systolic arrays or reconfigurable data flow units, maybe there's something about the latter.
Yeah, so we try to, when we build our core, so we have, whether it's an RT core or whether it's the tensor cores, we look at the computation we're performing and we do a real optimization to make that core very efficient, which usually involves coming up with a data flow, a way of feeding the data in at one side of the core and marching it through in a way that the minimum amount of data motion happens, and most of our energy can go into math and not into movement. And so I think that, we're, I'm trying to find that question up here. Another one popped up and scrolled it off of me or whatever, or maybe you deleted it or whatever. The other one was with reconfigurable things. So there is a
reconfigurable data flow units.
Right. And so there's a popular approach that many people are experimenting with called coarse grain reconfigurable arrays, CGRAs, and it's sort of a take on field programmable gate arrays where you're configuring at the gate level, and that's horribly inefficient. It's actually about 2 orders of magnitude inefficient on both area and power compared to actually building an ASIC for a given function. So people said, okay, we can get away with some of that by, rather than configuring at the gate level, let's build 16-bit arithmetic units and configure it at that level. And there's a startup company, 2 of my Stanford colleagues started, Chris Ray and Kunal Kotan, called Samba Nova, that's taking that approach. And they've been very successful, at least in the sense that they've raised a lot of money. I think they've raised like $1.5 billion. But ultimately, it's not more efficient than just building a good matrix multiply unit. And so, I think that I see the situation right now where it's a good thing in the sense that for a long time, you couldn't get a semiconductor startup company funded at all because the venture capitalists would look at it and say, look, you guys are going to be spending hundreds of millions of dollars before you get anywhere near to cash flow positive. And, the total market here is going to be X. And so there's no way we're going to get, even if you're wildly successful, we're going to get the 10X return on our investment we want out of funding you. And there's some probability you won't succeed, which is why we need the 10X. And deep learning has now sort of created this market that's big enough that they've funded something like 100 startups. I guarantee you all 100 are not going to succeed. But they all seem to have this premise. Some of them I think are doing the right thing, which is they're going after a narrow niche for embedded application, and they're combining application expertise and curated data sets and building an SoC for a particular application. I think they've got a good chance, but a lot of them are saying, okay, we're going to do generalized deep learning training. And it really boils down to doing a lot of matrix multiplies. And we do matrix multiplies really well. And then what you have to do is wrap everything else around that matrix multiply, which is really optimized data motion, which we do really well, and gobs of software. I mean, many thousands of person years of software to really fine tune this and to continue that as new neural networks come out. And I don't see any of them really having a value proposition, which is, we can do a better matrix multiply than the GPU, because our matrix multipliers are, within a pretty, 5 or 10% of, what we call speed of light, what you possibly could do.
Yep. Kevon has a question, although it's, let me just see if I could parse it. I think what he's getting at is, he says, because we have evolving humans with evolution, I think he's getting at maybe your more of an opinion. This sounds more philosophical about, given GPUs and AIs advancing, would you say that it'll evolve artificial consciousness? Maybe have a hand in that. That's what I'm guessing the question.
I think humans did evolve. To make the claim that we are still evolving, except maybe in Ukraine, there's not enough selection going on to actually have very much pressure on that. But I don't know that GPUs are really evolving with the performance. We're designing them to be faster every generation. And I think consciousness is this sort of concept of artificial general intelligence. And I think we're a long way from that. I mean, what we call AI today with deep learning is really building very, very good perceptual systems in most cases for speech or vision, building systems that are sort of data retrieval, data analysis systems for language. But I don't think they have consciousness in any real sense of the word. I guess we could try to define what consciousness means and design systems like that, but we're a long way away from that. I think it's kind of almost a different direction of research.
Yeah, the whole general AI is kind of a different thing. Dylan asks, is there any merit to analog front-end classification, for example, in voice activation, say Alexa, where you are dealing with an analog source?
Yeah, and I think that, I've not seen anybody actually make it work, but I think if you could avoid having to store anything and having to move anything, so you could keep everything completely analog while you had your wake-up network or whatever, you could potentially make it lower power than doing it digital. But what most people do these days is that they convert to digital and run some really cheap digital network on really low power hardware, and then wake up the big hardware to once they've recognized, hey Siri.